Hi, and welcome to my latest science chat. Tonight we have with us Professor Lisa Will. Welcome, Lisa. I
Well,
know you as a
thank
friend.
you.
I hope I can call you Lisa, but you also are Dr. Will.
You, of course, can call me Lisa.
Thank you. I'm honored. And I had met Lisa 3 years ago at a panel that we had, and I can't remember who hosted that, but it was a fun panel. We
I,
had we had people from IDW there.
yeah, it was when the Fleet Science Center and IDW were doing their crossover events.
That's
Yeah, that was a lot
yeah,
of fun.
that was fun. So, tonight I'm really excited because there's so much going on in space. I thought this was a perfect opportunity to have you on. It seems like there literally is something new every day. But first, I'll give folks out in the audience a chance to get to know who you are. And Dr. Will is an astrophysicist, educator, and geek. She is a professor of physics and astronomy at San Diego City College and is the resident astronomer of the Fleet Science Center in San Diego, California, which is fabulous. So I'm going to ask you some questions about your background, about what you do every day, and then dig into some space science and just hear the nuts and bolts of everything involved in your work. So, welcome again. And I first want to ask you probably the most obvious question. What made you wake up one day and go, I've got it. I'm going to be an astrophysicist and astronomy professor one day?
So it took a while for me to figure out the whole professor part, but I got interested in space via Star Trek as a kid. And I really honestly did think, well, exactly. I really honestly did think that we traveled in space before I knew we didn't.
Yeah.
And so I kind of had the disappointment, like, what do you mean Vulcans aren't real? What do you mean
Oh,
Starfleet isn't real? So I actually came to it from that, but it did make me interested in space itself. So I was the little kid at the library checking out the picture books of space and stuff like that.
Oh, I have good memories of that too, and
Yeah.
that's another reason I wanted to have you on is because I had such a strong interest in astronomy as a kid, and I ultimately chose life science. But there was a tipping point in which I was having to decide which way am I going to go, and
Yeah.
so since I didn't go, it's like the path not taken, right? So I'm always really fascinated to hear. Well, those of you who took the path, what was it like, and so what did you have to do to be able to do this? What sort of education did you have?
Well, let's see. I have a bachelor's of science in astrophysics from UCLA, and then after that, I got a PhD in physics, specializing in astrophysics at Arizona State. And that is sort of the typical path if you want to do astronomy as a profession. You have to go all the way through the PhD. It's not the only path, but it is one of the paths. And I'm glad I was such an obsessive nerd about it from a young age because that's part of what got me through. Because it's certainly not an easy path to take.
It's a lot of math, and a lot of long hours. And anybody going
Yeah.
for a PhD, it takes time, and
Yes.
and it can be, I would imagine, kind of isolating when you're doing the work. But at the same time, there's the appeal because you're doing what you love.
Yeah, I mean, and it definitely can be isolating, especially like I did sort of a computational astrophysics research project. So it really was just me and the computer
Yeah,
a lot of the times. But I think that's actually true in astronomy a lot. You're either doing computations or you're getting it to, do your image analysis and data processing. And so science is definitely a collaborative process, but so much of it actually is done on your own. And I think part of that's part of why I like teaching too, because that gave
oh
me
yeah,
more of the interaction with people.
that makes sense. Yeah, that would be really appealing. So I
Yeah.
guess you've probably seen an interesting mix of technology to get us to the point that we are today, in which we've now exited the solar system with the Voyager probes, and those things are basically at this point flying tin cans, and yet we have some really impressive space telescopes, which I will talk about in a moment. And so, but first, I want to kind of dig into, like, okay, what's your typical day like? You wake up, you go into work, and what is that like for you?
So, because I am a community college professor, it is primarily a teaching position. And so, and it's a full load. I teach This semester I'm teaching two different lecture courses, two different lab courses, and I'm teaching them online and in person.
Oh,
So yeah, the community college teaching keeps you busy. So my day started off with office hours and then a physics lecture and a physics lab. That's what teaching a physics lecture and a physics lab today. And so 5 hours of teaching after office hours. And so, but it's great. I really community college teaching is the best job in the world. I love the feeling of being somebody that helps open doors instead of being a gatekeeper. And I really feel like that's what our community colleges do.
oh, that's a really fantastic way to put it. Yes, and I just love that there are community colleges that offer, you know, what you do. So, and from there, you know, a student would go on and pursue an advanced degree, you know, and get
Yeah,
some
so
experience doing something. What would they do, you know?
well, so I one of the great things about teaching at a community college is that you have everyone from kids straight out of high school to older adults who are coming back and taking classes for fun. So I teach astronomy lecture and lab, which is mostly a GE course where I see a lot of adults taking it for fun. And then the physics I teach is typically for the pre-meds.
Okay.
And so many of them already have bachelor's degrees and are coming back to retrain and brush up to apply to med school. And then otherwise, I have students who have great success transferring into the UCs and getting into their undergraduate institutions that they want to get to so that they can go to med school. But a lot of my students, I think it would surprise a lot of people to find out that a lot of my physics students are actually applying directly to med school. They're going directly to grad school from community college because they got a degree, they figured out their career wasn't what they had wanted it to be, and then they're coming back and taking just the med school requirements. And that's about 25 to 30% of my physics students.
Would you
They're
say that that just related to that was has there been an increase in that in the last couple of years, do you think?
You know, being primarily online for the last 2 years definitely had a lot more people coming in that were working full time during the day, but could, sit through my physics lecture at 2 a.m. in the morning. And the average student, the age did skew a little older over the last two.
Okay.
You know me, I was looking at the data. I dredged up the data from the
I
last 2 years.
thought
And yeah, so we did see that, but that actually is something that ebbs and flows with the economy at the community college level too.
interesting.
Yeah.
It's pretty cool though, you know, and I've thought about going back and getting additional education, not just for my own personal, because you know I chose life science, you know, as I mentioned previously, and but there's part of me that itch is still there, you know, to kind of dig in a bit. So, and if you know, I've had advanced physics, but that was a long time ago. And so, you know, it would be nice to be able to kind of just really immerse in that environment, but also finally learn about what I really want to learn about, space. So,
Space.
and so you've described your typical day, and it sounds like a full day. And then, of course, you also you work as the resident astronomer for the Fleet Science Center in San Diego. So can you talk about that and what that entails? Which is pretty amazing because you're already a
Thank you.
teacher, a professor, a scientist, and then you go and you're the resident astronomer. What does that mean?
So, as the resident astronomer at the Fleet Science Center, primarily I do their live planetarium shows. And so do public outreach that way. I also contribute to their science blog. I do how should I put this news media appearances. So if there's something going on in
Oh,
space and
cool.
people call the fleet tags me, and so I do a lot of the space stuff around here. It was through the fleet that we started Astronomy on Tap here in San Diego.
Wonderful program.
So yeah, so it's primarily a science communication and public outreach job, which I love. And believe it or not, I got the gig from one of my community college students because when they needed a new person in that role, she had taken my astronomy lecture and she said, "Hey, I think my astronomy professor would be good at that."
Well, that's fantastic. I
Yeah.
well, and it speaks well of you. You left that impression, and she was like, she's perfect. So that's great. And what a gift to the community, too, to be able to do that because that is an all ages thing, being the resident astronomer, right, at the Science Center. And
Yeah.
except for the Astronomy on Tap, that is another all
Yeah.
adult thing. So, but, you know, having be able, you're able to move among these various audiences at various ages and backgrounds. I think that that's such a powerful thing for young people, particularly young women and girls who, might want to do this one day, but any young people at all, and that's just a fantastic, wonderful thing.
Well, thank you. I actually, all ages teaching, much like all ages writing, like writing middle grade is like writing for all ages, right?
Yeah.
That actually is to me more difficult, and requires a broader skill set than just coming into a classroom and saying, "Hey, kids, calculus was a prerequisite for this course, so here's an equation, have at it." And I actually found the first thing as a grad student I ever taught was physics, and then I taught astronomy, and I found teaching astronomy made me a better physics teacher because it taught me to emphasize concepts more and not rely on
Yeah.
the equations. And I feel like that's true with the all ages
Yeah.
approach, to be able to answer a 6-year old's question in a way that answers the 6-year old, but the 60-year old in the audience still gets something out of it, is a challenge that I enjoy.
I love that. And that it's just an impressive thing to be able to do and to pivot that way. So, God, I'm glad you're here. And in that regard too, like you have provided, being a consult for people, I guess writers, for example, to be able to ask you questions about feasibility and the science of it, and whether or not you're getting the science right or wrong, or
Yeah.
how ridiculous it is. I'm sure that you get taken out of your suspension of disbelief on the regular. So how do you deal with that when you're consuming science fiction, from a science point of view? I mean, I know what it does to me on the biology side. I'm just curious what you do.
Yeah, so that's a fantastic question, and I actually find that I can handle things being wrong in Star Wars more than Star Trek, because in Star Trek they have more of a presentation of being correct. And I'm just using those two as a comparison,
Right.
right? But I'm much more, if you push the magic warp drive button and don't try to explain to me how it works, I'm fine. That's a magic button that takes you faster than the speed of light. That's all good. And you try to explain to me why you can go faster than the speed of light, it's not as much. So I do have to turn that off sometimes, and sometimes you just can't, as you know.
Exactly, right. It's like watching Jurassic World. It's kind of like, well, okay.
For me, it was
Now,
those Mission to Mars and Red Planet movies that there were like a decade and a half ago or something
yeah.
now, and they were just like, it's like,
Now, related to that, instead of shows, do you are there particular books that you like, or have you read anything recently that really just ticked the boxes for you in terms of science fiction? You're like, yes, this is pretty good.
let's see, I've enjoyed Becky Chambers.
Oh, yes.
I've been really enjoying hers, and Anne Leckie,
Oh,
of
fabulous.
course,
Yep.
very much enjoy. And then in terms of TV shows, I've really been enjoying For All
Oh,
Mankind. Yeah,
a stan. I'm a stan for Frolic.
absolutely,
Oh,
absolutely.
one of the best things I've ever seen. I feel like, do you get this feeling that you feel like it was kind of made for us? That we were like, that's just, we always had that question, what would it have been like if, and then just,
Yeah, it's just a fascinating, like, yeah, it's just such a simple question. What if the Soviet Union had gotten to the moon first? Would we
right,
have stopped, or how would we have kept going? And the attention to detail is really interesting, and the way they've interwoven it with, it's a really good alternate universe, alternate
yeah.
history yeah. And the science isn't totally offensive, so
Right, right. There's a little bit of stretching, in parts, but by and large, it's a labor of love, as I like to describe it. You
yes.
can tell that they've done their best to honor the history and the science while still
Yeah.
keeping that drama and the uncertainty, because there's a lot that we don't know about how Mars is going to be, for example, in the future. How's that going to unfold? Maybe, hopefully, not to the level of drama seen in the show, but part of writing science fiction is so that we can help plan for true science in a way. We can sort of troubleshoot from storytelling. Wouldn't you agree?
Yeah, and that's actually one of the things I appreciate about that show in particular, is that the acknowledgement that space travel is hard. The And that space flight is hard and that we don't always get these missions off the ground the first time. And I think we went through such a period of successes that we don't um, that we get shocked when things fail.
Right.
And that shouldn't be it. Space is hard.
Yeah.
Whether you're launching an uncrewed spacecraft or you're preparing a rocket to send people to the moon next, you got to get it right.
Yeah.
And yeah, it doesn't always happen the first time.
Right. And it's that that's become quite relevant in the past couple of weeks with Artemis.
Yeah.
The problem with fuel leak, right? It was a fuel leak.
Yeah. Yeah, the first time it was like one of the engines didn't get up to the right temperature, and the
Right.
second time that was appears to be a fuel leak with the liquid helium,
Was
liquid
it helium?
hydrogen.
Okay.
Yeah. But what I think about that, the way I was trying to explain it to people is that the fact those launches got called off meant that the procedures worked, that
Exactly.
they caught it
Yeah.
before anything bad happened. Because those are big rockets, and you want them to get off the ground safely. So I try to reframe it that way. This meant that the procedures worked.
Right. Which is good. This is why you have these tests and these different redundancies.
Yes.
So yeah,
Yeah.
it's pretty important. We when tragedy has occurred, it has been often, bringing the question of like, well, what are we doing this? And like, there's a lot of questions about that. Oh, why are we going to the moon again? We've already been, but we haven't been since before I was born. I was born in '74, so we had just kind of wrapped up the moon stuff. And it's like, well, I mean, I know what I think about this and how important it is from my point of view, but I would like to know from your point of view how important it is that we go back to the moon.
I haven't really thought about it too much in terms of the moon. I would really like to get to Mars.
I know, same, but I have to, skip
Yeah.
the rock a little bit across the pond. So.
Yeah. For me, it's just that, especially relevant for Mars, the moon is 1.3 light seconds away. So if we're actually directing um, a rover on the moon, if we wanted to, you could almost do it in real time. But with Mars, you have like 20 to 40 minutes lag time each way. And so I think what you miss is the geologist's ability to catch a glint of the light off of a rock that you can't see with the rovers. Although the rovers are amazing.
They are.
Um, no disrespect meant to any of them, but I do think having somebody there with that sort of being able to see it in the moment, because the
Right.
light changes, the shadows changes, and we can't do um the the rovers when we work with them, they're it's not somebody with a joystick saying go that way. These are so planned out in advance. And yeah, I think we miss that spontaneity that really actually is important in science.
Right, and the ability to just begin experiments in person, which you just couldn't do with a rover, no matter what kind of robot you put there. It just would be better to have a person performing those experiments so we learn about living on Mars and what we can do. So it's a really interesting thing, to think that we kind of have to go back to the moon in order to be able to go to Mars. I don't know. It's up for debate. I feel conflicted about it.
Yeah.
I'm like you, but it's like we just go to Mars. But at the same time, I think that, there's the feeling that we need to inspire. And so let's get back to inspiring our young people today and talk about some of the pictures that have come out of this just wonderful space telescope.
Thank you. Thank you. JWST has, okay, I have to admit, I was a skeptic. It took so long to get off the ground and was so over budget, let's be frank. I was really, in the way it had to unfold in space, you had to have the sun shield unfold. There were so many things, and then everything, like more things went right than they
I
expected.
know.
So I'm willing to admit I was wrong. I'm really
I like it
um
when it's a good reason, right?
exactly. And the images have been stunning. Um
Gorgeous.
yeah.
You just
And
saw one today that was new that they released today, right?
so
Maybe they've already released it, but I just saw it today. So,
yeah, there's been a couple of different programs going on where there are the press releases that are fully realized,
right.
image processed, and then there's some other programs where they have some permission to do early release images. And so there were some early release images of the Orion Nebula that I saw floating around starting yesterday. And then there were some more beautiful Jupiter images. They've been taking images of Jupiter because JWST is an infrared telescope, not a visible light telescope. And so we're just getting, beautiful. It's just been nice to do proof of concept of how well we can do with it in the solar system. There had been some concern, like, would it be actually too bright? I mean,
Mm,
like how
yeah.
much detail would we see on Jupiter? And it turns out we're seeing a lot. So I'm very excited about that.
Well, in terms of excitement about JWST, let's talk about what else it's showing us out in the universe and what's got you really excited about that. I mean, I know, a little bit of lensing is happening, which is really neat to see. So, can we talk about that?
Yeah. So, in some of the first images, you might have noticed that there were some like little arc structures. And that was because one of the first sets of images was aimed at a galaxy cluster that is massive enough that its gravity can actually act as a gravitational lens. And so those little arcs are actually gravities, galaxies behind that cluster warped around so that you can see them. And that's something we've seen, before. We've seen gravitational lenses in space before, but that was a particularly prominent number of them
Right.
in that set of
Incredible.
images.
Yeah, just a
Yeah,
staggering number of galaxies. And you think, we're just a tiny little dot on the arm of a pretty big galaxy among
yeah.
all these galaxies. And it just, you feel tiny, but you feel part of something immense and wonderful and beautiful.
And that's one of the goals when I teach astronomy, is to make sure that one of the big things for me in teaching sort of your Astro 101 general education course is that, like, I don't care if you remember what causes the seasons or the phases of the moon 10 years down the road, but if you remember that we actually have the ability to figure stuff out. And
Yeah,
that's the big thing, that we have the ability to know, to determine things, even when these objects are so far away, we'll never be able to actually touch them.
right.
If you can remember that, then that I think is the important thing. It's a sort of a general science literacy course. Like, yes, we can do this. And so with JWST, one of the reasons it was always called a successor to Hubble, but so I've had people ask me, so why infrared? Why not visible light? And it's because the visible light from the most distant galaxies has been redshifted to the infrared. So when we see the really far away ones in the infrared, we're actually seeing their visible light. Yeah, it's wild. It's wild.
What else are we seeing that is really making the news in terms of what's out there?
So one of the other things that infrared light can do is it can penetrate through these clouds of gas and dust, these nebulae more deeply. And so some of the things you may have noticed when they've done comparison and contrast, like here's the Carina Nebula from Hubble versus here it is from JWST, you'll notice you see more points of light, you see more stars. And that's because you're actually seeing the star formation inside the
Cool.
nebula because the light from those protostars or those young stars can actually get through. One of the things that, okay, me personally, the thing I'm most interested in is the ability to get information about exoplanet
I was
atmospheres.
going to go there. Yeah,
That
let's
that
talk
that,
about
that
it. All right.
yeah.
Yes.
So the ways that we have mostly been able to look for exoplanets, which are planets that orbit stars other than the sun, is by the way they affect the light of their star. Either they transit it and block it, or they cause the star's light to get redshifted and blue shifted in a periodic fashion due to the gravity of the planet tugging on it. So we've been able to get things like the mass of the planet, the size of the planet. And if we're lucky, when they transit, there's that brief period when it's the planet's atmosphere going in front of its star, where you get the combined spectrum of the starlight and the planet. And we've been able to pick those apart. And they've actually already done that with JWST. So we have started to see some exoplanet atmospheres, including water vapor
Really cool.
and stuff. Yeah. And so then there was like organic chemistry compounds, and I was sending them to my chemistry faculty colleagues, going, "Look, we do fun chemistry in space," um, and tease them about that. But there is the possibility that we should be able to do direct spectroscopy of those
Yeah.
exoplanet atmospheres, which should be really interesting. And they also just showed their first direct imaging of a planet around a star
Yes.
too.
It's incredible. And I know, that's we're just going to see more of that, right? So,
Yeah.
and JWST is just looking at tiny points in our sky essentially. And just it blows your mind when you think about, well, they're finding planets, so many planets there, which they haven't even found all of them in that little spot. And you
Yeah.
think that is one pinpoint in the sky, in the entire sky that we can see, and then on the other side of the planet, and everywhere in all
Yeah.
directions. It just, we have a lot of planets in this galaxy alone, a lot. Some of them are gas giants, some of them are super Earths, some of them are smaller rocky things. We've got some in between action going on. We've got
Yeah.
some brown dwarfs floating around out there, and who knows what else we're going to find. So I find it incredibly exciting, and I geek out over it, not just because I'm curious whether we find proof of life, so to speak.
Hmm.
But it's just from a wonder standpoint, it's incredible the diversity of stuff we're seeing. And this is just the beginning.
Yeah, that's one of the things I like to emphasize is that when we study other solar systems and we study other stars and stuff, we're actually still studying ourselves. If we only ever studied our own solar system, we never would have guessed that Neptune-like planets were going to be the most common ones we'd find so far.
Yeah,
I
so far.
don't think
Yeah.
so far, uh, over 5,000 confirmed exoplanets so far. Yeah.
Now, related to that, do you think that it's that we're going to find? Do you think that there will ultimately? I mean, obviously, we don't know yet, but do you think, in terms of statistically, that there might be a lot more rocky planets? We just haven't detected them yet.
Absolutely. The observational bias in our methods in which we look for planets, they are biased towards large planets close to their stars because large planets have a longer or stronger gravitational tug
Right.
and they block more light. And the ones closer to their stars, in terms of the Doppler method, where we're seeing the red shifting and blue shifting, the closer they are, the faster they go around, and so the more likely we are to actually detect that wobble. So our bias currently is for large planets close to their stars, with the exception of direct imaging, which is large planets far from their stars. So all of our methods are biased towards large planets
Okay.
currently.
Gotcha.
So yeah, that's not a surprise. It's one of those cases where you have to understand what what is how is our experimental setup? What is it going to be best at? And that observational bias. With the Kepler spacecraft, its original name, you know how they do those working names and then they name them
Yes.
after something. It was Terrestrial Planet Finder, so
Oh,
it was meant to find Earths, and it did. It did. It found planets down, rocky planets down to the size of like Mercury-ish. Yeah,
which is pretty impressive.
yeah,
But
absolutely.
Mercury is not large,
It's
so
not large.
in fact, we have asteroids that are larger than Mercury in
uh,
our
we
solar system, right? So,
we definitely have a couple moons about the size of Mercury or larger. So yeah,
how
the
does Ceres compare to Mercury?
Ceres is still smaller.
Still
It
small.
is
Okay.
still
All right.
smaller. Yeah, but Ganymede, the largest moon in the solar system, the largest moon of Jupiter, is actually larger than Mercury, and then Titan and Callisto are about the size
Same
of
size.
Mercury. Yeah.
All right.
So if we just threw them around the sun, you'd be like, "Hey, look, it's a planet," and you wouldn't.
Right. Right. And so, like we have a lot of bodies, celestial bodies in our solar system that
Hmm.
are considered dwarf planets. And while this is more planetary science than astronomy, it's still related, right? So we're studying these different heavenly bodies, and with we're finding a lot of interesting things about them. And series bringing up series again, that we saw some
Hmm.
interesting visual aspects on that, and we're sort of like, what are we seeing there? Like things like that.
So on Ceres, we saw this sort of bright, reflective region, and so the first thing you think of is going to be ice, but it turns out to have been like a briny, salt watery type ice that seems to be getting replenished from beneath the surface. So that speaks to an activity that we did not expect of something that small. So that caught a lot of people off guard, but was kind of fun. So you know how you said you were kind of torn between life science and astronomy. For me, it was sort of geology versus
Yeah.
astronomy. So planetary science, even though that's not what I went into, it's one of my things. I love teaching the
Awesome.
solar system. So yeah. And so yeah, when the Dawn spacecraft approached Ceres and you could actually see those white splotches. And they even changed over time when we were
Yeah, it
watching them.
was pretty
Yeah.
neat.
Yeah.
And it's just a really exciting time for space exploration in general. So, what are you most looking forward to in terms of what's coming?
There is a tiny, I don't want to call it a tiny mission, but it's one you might not have heard of. It got greenlit a couple years ago before all this happened, and it's the Dragonfly mission,
Okay,
um,
I have heard of
which is a mission that will go to Titan, the largest moon of Saturn, and the moon with an extensive nitrogen atmosphere, a denser one than the Earth's. And it has a quadcopter. And so instead of being a rover, it's going to be a flying science laboratory. The goal is it will land somewhere, it'll do its thing, and they'll be like, okay, where to next? It's like, oh, we're going to fly there.
it. So,
So the little helicopter that's been flying on Mars with the latest rover there is kind of proof of concept that you can actually do that in a thin atmosphere like Mars.
yeah,
And so a denser atmosphere like Titan should be no problem then.
excellent. That'll
Yeah.
be so cool. When is this coming? When is it being?
The original goal was later this decade because these missions not only do they take a while to get built after they get funded, but Saturn it takes a few years to get to.
A
And
while. Yeah,
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 far out there. It's because, you have the inner worlds, of, Mercury, Venus, Earth, Mars. Then you have this giant asteroid belt. And then you
yeah,
have the big guys, the big gas giants in the outer solar system. So that's a whole lot of real estate to cover. And
it
yeah,
is.
I wish that we could do it faster and get there faster, but that isn't the way it works. We don't have warp drive.
We
So,
don't have warp drive, and that's why sometimes people ask if why did New Horizons do a flyby mission of Pluto? Why didn't it stay there? And it's like, well, because to get it out there in a reasonable amount of time, it had to go so fast that Pluto couldn't capture it with its gravity. So
right,
you had your choice of get out there and get pictures or, you know, take a long time. And
right,
that's kind of the problem with the exploration of the outer solar system. I mean, only Voyager 2 has gone to Uranus and Neptune yet.
right. It would be just amazing to see. I'm kind of really eager to see Neptune again. It's such a beautiful planet, the beautiful blue. And so love to
Yeah.
see that again in my lifetime. And
Yeah, me too. And the moons of Uranus and Neptune are probably, when we finally saw the moons of Pluto, its largest moon, Charon, really reminded people of like the moons of Uranus and stuff like that.
yeah,
And so it could be that instead of getting all the way back out to the Pluto system, if we sent a spacecraft to Uranus and studied its moons, some of those moons could be captured Kuiper Belt objects. You know,
yeah.
yeah. So I kind of wish we could do that too.
I know. And so can we talk about Kuiper Belt objects? And what is the difference between the Kuiper Belt and the Oort cloud for those who don't know? Let's talk about both if you don't mind.
Of course. So the objects in our solar system, you've got the planets, then you got the big asteroid belt between Mars and Jupiter. And then further out in the solar system, we have sort of a donut shape, ring of objects called the Kuiper Belt that starts at about the orbit of Neptune and extends pretty far. I mean, think of the distance between the sun and Uranus. And that would be sort of the width of the Kuiper Belt. So you got this big donut or torus of these objects. So Pluto's out there in that. And these are these large icy objects. And it's also the home of the short period comets. So comets come to us from out there. And we've got images of stuff out there. The Oort cloud is this large spherical cloud of icy objects that we know exists because of the orbital patterns we see of the long period comets, the ones that take thousands, hundreds of thousands of years to orbit the sun. So we only see them like once in a human lifetime, but they come in at extreme angles. And if you connect the dots to complete their ellipse, they take you really far out there. And so, yeah, we've never been able to photograph anything out in the Oort cloud because it is a huge spherical cloud, probably left over from the formation of our solar system. Yeah. Whereas the Kuiper Belt, that's one of the things that the Hubble Space Telescope, like I was an undergrad when Hubble was going to be launched.
Yeah.
And so like when I took the classes I teach, hadn't seen stuff out there yet. So it's been kind of fun to see how much things have changed. And yeah, so we've got this huge reservoir of icy objects in the outer solar system.
Which is pretty interesting. So we have a lot of there's a lot of water in our solar system that
Mhm.
is not on Earth.
Yes.
And what can you tell us about that?
Water is common in the solar system. It turns out it's just in the form of ice typically. As icy surfaces of moons in the outer solar system, in comets, the we do see evidence for liquid water, but the Earth is the only place we see evidence for liquid water on the surface for any significant amount of time. But we have Europa, one of the moons of Jupiter, and Enceladus, one of the moons of Saturn. Both of them definitely have liquid water beneath their surfaces. And so, Enceladus has liquid water geyser activity that we could just
So
see with
cool.
the Cassini mission. Yeah.
Yeah.
And Hubble has caught hints of geyser activity on Europa, actually. Like you see these little wispy things. So we know there's water out there. It's just not in the most convenient form for us. Like, oh, look, there's a nice lake on Mars. We could just go to Mars and not have to worry about finding water. Oh, Mars has ice caps that are CO2 and water ice combinations, and it's got some water vapor in the clouds and probably um, water underneath its surface somewhere, but not on the surface for any reasonable amount of time, at least nowadays.
Right. Because you can see, with your geology interest, you see the movement of liquid, the shape of the land and how it was carved by erosion on Mars. So at some point,
Absolutely.
it was absolutely shaped by it. So it's really interesting to think that while it isn't there anymore, could it be beneath the surface? How far down? What would it be like? What temperature is it? Those kinds of things. So that's part of the
Mhm.
reason we want to go to Mars.
Yeah.
It's-
Yeah. If it's underneath the surface, is it what we would call fresh water anymore? How much would we have to treat it? Would it be briny like what we think we're seeing on Ceres and so on, where we're basically looking at a saltwater reservoir instead?
yeah,
Um, yeah. But it is interesting to look throughout the solar system, and you know it is what makes the Earth pop out when you look at images, right? It's the blue of the oceans, and we just don't see that elsewhere in the solar system. But in the last couple of decades, we've definitely picked up indications that the water is out there plentifully. It's just, whether or not it and whether or not we want to or can use it for ourselves.
yeah, because there comes a point where how much energy would you need to use and what equipment would you need to use to make it potable, to make it usable for our purposes versus.
Yeah.
So,
Or like the idea of terraforming Mars by crashing comets into it. That's not exactly the most energy easy thing
that would be
to do.
quite challenging, if not
Yeah.
possible, which at this point in time, we can't even feasibly think about that. So,
Nope.
but I want to go back. We were talking about atmospheres of exoplanets.
Hmm.
So there's been a lot of talk of things that we could detect in them that might indicate that there would be life as we know it. And what would be some of those things that we would look for? And what would you see that would be like, ooh, okay, my ears are tingling now.
So
Get the
honestly, yeah.
ears on.
So honestly, it just if you just compare it to our solar system, the thing that pops out in the Earth's atmosphere that you don't really see plentifully on any of the other planets with atmospheres in our solar system is just molecular oxygen, the sheer amount of O2 in our atmosphere, which we think was basically respirated
Hmm.
here, right? So if we saw abundant O2 in an atmosphere, if we just doing good old comparative planetology, like if how did it work here versus how would it work there, the most likely thing could be life, organisms that are breathing in carbon dioxide and exhalating, you know,
Yeah.
O2, which is basically what, we think if you take a look at the terrestrial planets, Mars and Venus mostly have CO2 and then nitrogen in their atmospheres. We're the outlier, but we probably started off all with identical atmospheres. And it was just the distance from the sun that
Right.
allowed the water cycle to occur here and for life as we know it to actually alter the atmosphere.
Well, it's going to be really interesting to see what we pick up, with the new telescopes and things like that. So, I mean, do you It's just throwing a dart and saying, how likely do you think it is that we're going to see a signature that makes us go, well, like we have a lot of planets out there, but it's like there's, I don't know, like statistically versus what we wish. I know that what we wish is we want to find more of us in a situation. It wouldn't be us. We wouldn't have
Right.
like bipedal probably organisms or whatever. We might have microorganisms, even on, Europa in the subsurface,
Right.
extremophiles, but out there,
So the way I usually describe it, because I am not a life scientist, but the way I usually describe it is that if I were to give the chemistry of space to a life scientist colleague and say, "Can you make life out of this?" Your answer would be yes.
yeah, there's a
Because
lot of carbon out there for one thing.
yeah, good
Also,
old what?
we carbon's
Tron, right?
abundant, so you think carbon
Right.
instead of like silicon or whatever. It would be more likely be carbon based.
Right. And so the carbon, hydrogen, oxygen, nitrogen that we see as being so crucial to our biology here in on Earth is abundant out in space. And so whether or not we find it is one thing to me, whether or not it's out there is another. I feel confident that there has to be life out there somewhere. It's just space
Statistically
is, yeah, just
huge.
but space is big and we are small.
Right.
So like our ability to find it is what's limited. If we were the only life, if we were the only planet with life, I would find that extremely discomforting. Like,
It would be it would be disturbing, right?
yes,
Like,
absolutely.
which, and then we couldn't even prove that, right? So,
Yeah. But right now, like with our technology, people looking back at our solar system would still have, a hard time I just try to think of what would we see using our current technology if we were around another star looking back at our solar system. The Earth's atmosphere would still be really hard to
yeah,
notice.
yeah.
So we would be a solar system comprised of Jupiter and the sun for the
Right.
most part, from people on the outside looking in. So I'm just trying to be patient. I think JWST definitely has increased our odds of discovering it, but yeah, especially since looking at atmospheres in the infrared, because of the way molecules absorb and emit light, they
Yeah.
have a lot more signature in the infrared than they do in visible light. So we're likely to see some of those. So I'm looking forward to it.
Well, okay, so then one more thing kind of related to that. How much do you think artificial intelligence will help us in this search? How much is it helping us now? How much do you think it'll help?
So I've had, friends and colleagues over the years try to do things like use AI and neural networks and things like that to actually try to go through large data sets
Right.
to do the first run of identifying interesting signatures. But in the end, they always take the flagged interesting things and hand it over to people
Yeah.
to look at, right? So that could it be something that helps us? Yes, but I still think that in the end, we still go to our expertise and the thing about our brains that is good at pattern
I was
recognition
going to
and
say
then
pattern recognition. Yep.
absolutely and that notices when
That's
something's
something I'm
wrong.
really good at myself, and like it can be visual, audio, or tactile. It just seems some of us are just that's what we do, It's how we survived this long, you know.
Absolutely. And pattern recognition is a big thing for me too.
Yeah.
And I think the thing when you do these, when you train your AI and stuff like that, you're training them to recognize the patterns. If you feed them patterns, are they going to be as good at recognizing the outliers as our brain is? Because I think that's where we excel. So yeah, but I, I don't know where the answers are going to come from on that. I just hope to see them.
I do too. I really do. So, I this has been a wonderful hour, and I'd love to ask you, is there anything that I've not discussed that you'd like to bring up that would be interesting to pass on to our listeners and viewers?
My brain always just stops at this point when I try to think of anything interesting. Just to expect more JWST images to start coming out more quickly.
Yes. Wait.
as because most of the scientists, most of the PIs did not actually get their data until the week that we all first saw the first images. Those first images were taken in May, and then there was a lot of effort put into getting those images out. But that same week, I had friends uh, get the email that contained all of the data from their first set of observations, and there's still people working through that
Well,
stuff.
yeah,
And so
that's a
more
lot
and
of
more
data.
stuff is going to start
Yeah, okay.
coming out.
Great.
Mm, yeah.
Well, that's good news for all of us, and I think it's captivated a whole new set of people of every age, and I think that social media has come in handy for at least that much that we can share in the excitement of space and science, and it's a really good time for both. So I'm so glad we have you and that you can help teach us about the universe. So,
Well, thank you. Like I said, being able to do this sort of science communication, especially using astronomy, is really a lot of fun. I feel like it's the best job in the world. And I thank people like you for having me on to chat about it and to reach another audience.
well, thank you so much for coming, Lisa. And where can we find you online?
So I'm on Twitter at DustChick. That's mostly where I rant about things, including astronomy and promoting astronomy. Also on Instagram, AOTSD, Astronomy on Tap San Diego, for things like that. Fleets on Twitter, Fleet Science, for the Fleet Science Center and supporting their programs, and also SD City College on Twitter for San Diego City College, where if you come take an astronomy lecture there, we teach it in a planetarium.
Candy.
Gotta say.
Awesome. Dr. Lisa Will, thank you so much for being on Science Chat and Ad Astra, and live long and prosper too, fellow.
Thank you.
Take care.
You too.